You live your life believing that time is the fundamental beat behind everything. But when physicists wrote down the master equation for the entire quantum universe, the letter T for time completely disappeared. The most fundamental formula we have says the universe does not flow, it simply exists. To understand why time is missing from the master equation, we need three things: the wheeler-dewitt equation, quantum cosmology, and the problem of time. Now, let us step in. Look at a clock. Any clock. The one on your wall, the numbers on your phone, the watch on your wrist. Watch 1 full second pass. There. The universe just got 1 second older, and so did you. And nothing in your entire experience is more obvious than what just happened. Time passed. You could doubt almost anything before you doubted that. You could doubt what you see. Optical illusions exist. You could doubt what you remember. Memory fails. But that 1 second went by. That the moment you are in right now is already becoming the past. Doubting that feels like doubting that anything exists at all. It passes whether you watch or not. It passed before you were born, and it will keep passing after you are gone. A great impartial river carrying everything from was to is to will be. Of all the things physics could take away from you, this one feels the safest. So let me show you how seriously physics takes clocks before I show you what it did to time. In a laboratory in Boulder, Colorado, at an institute called JILA, stands the most accurate clock our species has ever constructed. It does not tick with gears. It counts the impossibly fast vibrations of strontium atoms held in a lattice of laser light, and in 2024, its builders published its performance. A total systematic uncertainty of 8.1 times 10 to the minus 19. Written plainly, that is a precision equivalent to a fraction of a second over the entire age of the universe. This machine is so sensitive to the texture of time that it can detect something almost unbelievable. Raise part of it 1 single centimeter, the width of your fingernail, and it measures time flowing at a detectably different rate in that centimeter, because gravity runs infinitesimally weaker 1 centimeter up. We have built an instrument that reads the flow of time off a fingernail's height of gravity. That is how real time is to physics. That is how measurable, how physical, how solid. Now here is the fact this entire video exists to confront. Behind quantum mechanics and general relativity, our two supreme theories, there is a deeper equation. The one you get when you force those two theories to merge into a single quantum description of the whole universe. It is called the wheeler-dewitt equation, and it is the closest thing physics has to a master equation of everything that exists. And in that equation, the letter T, time, the quantity our Boulder clock measures to 19 decimal places, the river that carried you from your childhood to this sentence, appears exactly 0 times. Not approximately 0, 0. The equation reads in full, h hat psi equals 0. The state of the entire universe, acted on by the total energy operator, gives nothing. No change, no flow, no before and no after. The most fundamental formula we possess describes a universe that simply, statically, timelessly is. Hold both of those facts in your hands at once. The clock that reads time off a centimeter of gravity, and the master equation in which time does not exist. Because the collision between them is the deepest open wound in theoretical physics. It has a name, the problem of time. And by the end of tonight, you will understand exactly how the letter T vanished, step by mathematical step, and why the disappearance was not a mistake, but an unavoidable consequence of the two theories we trust most. Then comes the truly strange part. 5 different ways physicists have found to get time back, including a laboratory experiment in Turin that built a tiny frozen universe out of 2 particles of light and watched time emerge inside it like a ghost. The story begins, as these stories often do, 3.5 centuries ago, with the man who told us time was absolute, and wrote the definition so persuasively that you still believe it, and the man who took that away. In 1687, Isaac Newton published the Principia, and in its opening pages he defined the stage on which all of his physics would perform. Absolute, true and mathematical time, of itself and from its own nature, flows equably, without relation to anything external. Read that again slowly, because it is your own belief, written down 3.5 centuries ago with perfect confidence. Time flows, by itself, the same everywhere, needing nothing. Every clock merely samples it the way a bucket samples a river. For 228 years, that sentence sat beneath all of physics as its silent foundation, and beneath every human life as the obvious truth nobody thought to question. Einstein questioned it. In 1915, general relativity replaced Newton's rigid stage with something alive, space-time, a four-dimensional fabric that bends under mass and energy, in which the rate of a clock depends on where it sits and how it moves. This is not philosophy, it has been measured to exhaustion. In 1971, two physicists named Haffel and Keating packed 4 atomic clocks onto ordinary commercial airliners and flew them around the world, then compared them with clocks that had stayed home. The traveling clocks came back carrying different amounts of elapsed time, mere billionths of a second, but exactly the amounts relativity predicted. Today, your phone's navigation performs this correction constantly. The clocks aboard GPS satellites run measurably differently from clocks on the ground, and if the correction was switched off, your position would drift kilometers per day. And the Boulder clock has now dragged the same fact down to a single centimeter of height. Time, after Einstein, is not the river Newton described. It is local, flexible, physical, part of the machinery of the world, not the stage beneath it. And relativity hides a second blade, one that cuts closer to tonight's wound than the bending of clock rates. The death of the universal now. In Newton's world, right now, everywhere, is a meaningful sentence. One great simultaneous instant slicing across all of existence. Einstein showed the slice is observer-dependent. Two travelers in relative motion, passing each other at this very moment, disagree about which distant events are happening now, and both are correct, because space-time contains no fact of the matter. There is no universal present moment. The four-dimensional whole simply exists, and each observer's now is their own private cross-section of it, real to them, meaningless to the universe. Physicists call this the block universe picture, and notice how far it already goes toward tonight's abyss. Even before quantum mechanics enters, relativity had quietly dissolved the single flowing present into a democracy of personal slicings. What the wheeler-dewitt equation will do is finish the thought. Take the theory whose deep grammar says all slicings are equal, marry it to quantum mechanics, and watch the marriage delete the ticking altogether. But notice what even Einstein did not do. In general relativity, time still exists. It bends, it stretches, it disagrees from place to place, but it is there, woven into the fabric, one of the four directions of space-time. And in the other great theory of the 20th century, quantum mechanics, time is even more traditional. The central equation of the quantum world, written by Erwin Schrödinger in 1926, is built around time in the most explicit way possible. Spoken aloud, the Schrödinger equation says, IH bar times the rate of change of the wave function in time equals the Hamiltonian acting on the wave function. Never mind every symbol for now, hear the structure. The left side of the equation is nothing but change in time. The equation's entire job is to tell you how the quantum state evolves from this moment to the next. Quantum mechanics without its time derivative would be a car without an engine. Time is not decoration in these theories, it is the drivetrain. So now put yourself in the shoes of the physicists of the mid-20th century, holding one theory where space-time bends and another where quantum states evolve, and facing the obvious next mountain. Merge them. Quantize gravity. Write the quantum theory of space-time itself. the equation for the wave function not of an electron, not of an atom, but of the entire universe. Every expectation said the result would look like a grander Schrödinger equation, some cosmic state evolving majestically in time. That is what everyone was building toward. What they got instead is the reason you are watching this video. And one more voice from the room you should meet before we open the equations. The belief itself deserves its dignity. If you have ever felt that questioning the flow of time is a game for people with too much chalk, understand that your conviction has impeccable credentials. Every equation you were ever taught has T in it. Every experiment you ever ran logged its data against a clock. Every branch of science, chemistry with its reaction rates, biology with its generations, astronomy with its light years, is built on temporal bedrock. The belief that time flows is not a folk superstition physics is about to correct. It is the load-bearing assumption of physics' own entire history. That is what makes what follows so vertiginous. The challenge to time did not come from outside science, from mystics or philosophers. It came from the two most successful theories science has ever produced, the moment someone forced them to speak to each other honestly. The road to the master equation runs through a small conference in 1957 in Chapel Hill, North Carolina, where the scattered physicists who cared about gravity gathered to take stock. The gathering itself deserves a sentence. General relativity in the 1950s was a backwater, magnificent, confirmed, and largely abandoned, its practitioners scattered thin while the age's talent chased particles and fields. Chapel Hill is where the exiles regrouped, and among the questions circulating in those rooms was a graduate student's outrageous thesis, Hugh Everett's relative state formulation, the ancestor of the many worlds interpretation, with its then heretical centerpiece, a wave function for the entire universe, observers included. The phrase wave function of the universe, which tonight's whole story orbits, entered physics breathing the air of that conference. In those rooms was John Archibald Wheeler, the same Wheeler who named black holes, who mentored Richard Feynman, whose habit of asking outrageous questions in complete sincerity shaped a generation of physics. Wheeler had become gripped by a vision he called geometrodynamics. Treat the geometry of space itself as the dynamical object, a thing that changes, carries energy, obeys equations, and then do to that geometry what Schrödinger did to the electron. Wheeler imagined the space of all possible three-dimensional shapes of the universe. He called it superspace, and a wave rolling across it. A wave function whose value at each possible geometry says how much that shape of space participates in reality. One of the physicists in Wheeler's orbit in those years, a precise, formidable theorist named Bryce DeWitt, would eventually be the one to write the wave's equation down. Keep both names. The equation wears them jointly. Stop on Wheeler's superspace for a moment, because the picture is worth owning before the mathematics arrives. Take every possible shape that three-dimensional space could have, every wrinkle, every curvature, every cosmic architecture, from perfectly smooth emptiness to geometries crumpled beyond imagining. Now treat each entire shape as a single point in a vaster landscape. That landscape, one point per possible geometry of the whole universe, is superspace, and it is monstrously infinite. Since a geometry can differ at every location in space, superspace has infinitely many dimensions, a coordinate for every point of the cosmos. Wheeler's proposal was that quantum gravity is a wave on that landscape, a wave function assigning an amplitude to every possible shape of space at once. Where the wave is large, that geometry is strongly represented in reality. Where it vanishes, that shape of space is not happening. Notice what is absent from this picture from the very beginning: a movie. Classical physics describes the universe as a film strip, geometry after geometry, projected in sequence. Wheeler's quantum picture describes it as a single, standing wave over all possible frames simultaneously. The film cans are all open on the table at once. Nothing in the formalism threads them onto a reel. But before anyone could quantize gravity, general relativity itself had to be rebuilt into the right shape. And this rebuild, finished between 1959 and 1962 by Richard Arnowitz, Stanley Deser, and Charles Meisner, is where the seed of the strangeness was planted. Their construction is known by their initials, the ADM formalism. What they did sounds almost innocent. Einstein's theory treats space-time as one four-dimensional block. The equations do not naturally separate space from time. Arnowitz, Deser, and Meisner sliced the block. Picture a loaf of bread. The whole loaf is space-time, and the ADM move is to cut it into a stack of thin slices, each slice being all of space at one instant. Evolution in this picture means stepping from one slice to the next, and the machinery that describes the stepping has two adjustable pieces with wonderfully plain names. The lapse tells you how much time elapses between one slice and the next at each point. The shift tells you how the coordinates slide sideways as you step. Lapse and shift are the bookkeeping of slicing, how thick you cut and at what angle. Before I show you what the slicing revealed, you need one piece of machinery, because the entire catastrophe happens inside it. In the deep formulation of mechanics, the one physicists actually use, every theory has a single master function called the Hamiltonian. For ordinary systems, it is simply the total energy, but its true job is grander. The Hamiltonian is the engine of time. Feed it the state of a system now, and it generates the state a moment later. It is the mathematical object that pushes the world from each instant to the next. When Schrödinger's equation says IH bar d psi dt equals h hat psi, it is saying exactly this. The rate at which the quantum state changes is dictated by the Hamiltonian. No Hamiltonian, no push. Zero Hamiltonian, zero push. Keep your eye on that engine, because you are about to watch general relativity dismantle it. There is one more piece, humbler still. What happens in mechanics when a theory contains a variable it does not actually care about? Think of a ledger with a column nobody audits. The theory's equations place no dynamics on it, no momentum, no pushback. Mathematics has a name for such variables, Lagrange multipliers, and a standard verdict about them. They are not participants in the physics, but enforcers of conditions. When you vary the equations with respect to an audited dynamical variable, you get a law of motion. When you vary them with respect to an unaudited multiplier, you get a constraint, a demand that some combination of the real variables must equal zero, always. Multipliers do not evolve, they compel. And here is the discovery that changes everything, the technical heartbeat of this whole video, so I will give it to you first in plain words. When Arnowitz, Deser, and Meisner wrote general relativity in this sliced form and examined the equations, the lapse and the shift turned out to have no dynamics of their own. Nothing in the equations pushes them around. Nothing determines them. The theory is completely indifferent to how you slice. And in the mathematics of mechanics, a variable the theory is indifferent to is not a participant. It is a free choice, and the equations respond to a free choice by issuing a constraint, a condition that must be satisfied rather than an evolution that unfolds. When the dust settled, general relativity delivered its verdict in the strangest possible form. The total energy function of the gravitational universe, the Hamiltonian, the very object that in every other theory generates change in time, is not a quantity that takes some value and drives evolution. It is a sum of constraints. And on any physically allowed configuration, it equals exactly zero. Let me say that more plainly, because it is the sentence the rest of tonight stands on. In a universe governed by general relativity, taken as a whole, the total Hamiltonian is zero. Not small, not conserved at some value. Zero, identically, always. Because the theory refuses to prefer any slicing of spacetime, and that refusal, fed through the machinery of mechanics, forces the generator of time evolution to vanish. The thing that would have made the universe's clock tick is constrained to nothing. Why does the refusal to prefer a slicing do that? Here is the intuition, and it is worth 30 seconds of slow thought. In Newton's world, time is a real river, so advance the universe by 1 second is a genuine operation. Something actually happens. In Einstein's world, a second is just a label on a slice, and the slicing was your free choice. Advancing the universe from one slice to the next is therefore not a physical change. It is a relabeling, like flipping through differently cropped photographs of the same sculpture. The sculpture does not change, and the mathematics knows it. The operation that advances time is revealed to be a gauge transformation, a change of description, not a change of world. The Hamiltonian generates that operation, and the generator of a do-nothing operation must be zero. General relativity is not a theory in which time flows and things evolve. It is a theory in which the four-dimensional whole simply is, and evolution is how the whole looks when you insist on reading it slice by slice. If the ADM machinery sounds like abstract carpentry, know that it has since been vindicated in the most spectacular way physics allows. The same 3+1 slicing, the same laps, the same shift, the same constraint equations, is the computational backbone of numerical relativity, the discipline of simulating Einstein's equations on supercomputers. When two black holes spiral together and merge, the gravitational waveform they broadcast is computed by evolving ADM-descended equations slice by slice. And on September 14, 2015, the LIGO detectors heard exactly such a waveform arrive from 1 billion light-years away, the first direct detection of gravitational waves, matching the sliced spacetime computations to stunning precision. Remember that when the freeze arrives. The formalism that deletes time from the quantum universe is not some fragile speculative scaffold. In its classical regime, it has touched data as hard as data gets. That is precisely what makes its quantum verdict so difficult to dismiss. A word on the man who turned the crank, because the field he founded remembers him with awe, and he is too little known outside it. Bryce Seligman DeWitt, born 1923, was the opposite of a popularizer, a theorist of legendary rigor and stamina who took on the computations others declared impossible. Together with his wife and collaborator Cecile DeWitt Moret, a formidable mathematical physicist who organized the Chapel Hill Conference itself, he effectively willed the field of quantum gravity into existence when almost nobody considered it a career. His 1967 masterwork was not one paper but a trilogy, laying out in a single sustained campaign the canonical theory, the frozen equation, and the covariant machinery that modern quantum gravity still runs on. He lived until 2004, long enough to watch his equation become the field's foundation stone and its favorite scandal at once. At the classical level, Einstein's level, you can shrug this off as formal bookkeeping, because you can always pick a slicing and compute, and rivers and clocks and planets come out moving as they should. But in 1967, Bryce DeWitt did the thing everyone knew had to be done. He took the sliced, constrained form of general relativity and pushed it through the standard machinery of quantization, the same crank-turning in principle that turns classical mechanics into quantum mechanics. In quantum theory, a classical constraint becomes an operator condition on the state. Whatever the constraint forced to zero classically, the corresponding operator must annihilate the wave function. The classical Hamiltonian of the universe was zero, so its quantum operator, acting on the wave function of the universe, must give zero. Write it down. The Hamiltonian operator, h hat, the wave function of the entire universe, psi, and the equation, h hat psi equals 0. Set it beside Schrödinger's equation and look at the wound. Schrödinger, IH bar d psi dt equals h hat psi. Wheeler-DeWitt, h hat psi equals 0. It is the same equation with the entire left-hand side, the time side, amputated. Not approximated away, not hidden. Structurally absent, because the object that would have paired with the time derivative was constrained to 0 before quantization ever began. DeWitt published it in Physical Review in 1967 in a paper titled Quantum Theory of Gravity, and he initially called it the Einstein-Schrödinger equation. The community soon named it after Wheeler and DeWitt jointly. It is reportedly said that DeWitt himself came to speak of it wearily. The folklore has him calling it that damned equation, though I flag honestly that this is lore, not a documented quotation. What is documented is how the literature describes it. Infamous, notorious. An equation whose state, as one review put it, appears to be stationary, contrary to obvious everyday evidence. Let me make sure the mechanism has truly landed, because it is the one piece of hard machinery this video asks you to own, and it can be said in 4 steps of plain language. Step 1. General relativity does not care how you slice space-time into moments. All slicings are equally valid, none is real. Step 2. In the mathematics of mechanics, advancing from slice to slice is generated by the Hamiltonian, and since the advance is merely a relabeling, its generator must vanish. The Hamiltonian of the whole universe equals 0. Step 3. Quantum mechanics converts every classical constraint into a sentence about the wave function. Whatever was forced to 0 must, as an operator, annihilate the state. Step 4. Therefore, h hat psi equals 0, and since the Hamiltonian is also the engine of the Schrödinger equation's time derivative, a 0 engine means no time derivative at all. Symmetry, to constraint, to quantization, to freeze. 4 dominoes, each fall almost trivial, and at the end of the chain the master equation of the universe stands with no clock in it. If you followed that, you understand the problem of time more honestly than most popular accounts will ever show you. Because you have seen that it is not an exotic postulate, but a collision of the 2 most boring, best confirmed principles in physics. Sit with what it claims. The wave function of the universe, the complete quantum description of everything. Every field, every particle, every galaxy, you, your memories, this moment, does not evolve. There is no T for it to evolve in. Asked, what does the universe do? The deepest equation we have answers, nothing. It does not do. It is. Every sunrise, every heartbeat, every second your Boulder clock so exquisitely counts, none of it appears in the fundamental description. The universe, according to its own master equation, is a single, frozen, timeless quantum state. Physicists call this the frozen formalism, and the scandal it creates has the name I gave you at the start, the problem of time. It is not a fringe puzzle. It follows directly, almost mechanically, from the 2 most successful theories in the history of science. If general relativity is right about covariance, and quantum mechanics is right about quantization, then at the deepest level, time is not there. If you are enjoying how deep this is going, we are only at the entrance of the cave, and the strangest chambers are ahead. Take 1 second to press subscribe, so the channel can keep making journeys like this one. Now back to the frozen universe, because I owe you 3 honest complications before we go hunting for lost time. Complication 1. The equation is not even fully well defined. In its complete form, the wheeler-dewitt equation lives on superspace, Wheeler's space of all possible shapes of the universe, which has infinitely many dimensions, one for the geometry at every point of space. On that arena, nobody has ever constructed the full rigorous mathematics. There are unresolved ambiguities in how to order the operators, and no agreed way to define the probabilities that quantum mechanics is supposed to deliver. The equation is a blueprint more than a finished building. Complication 2. To compute anything at all, physicists shrink the arena drastically, a maneuver called mini-superspace, freezing all but a handful of variables, typically just the overall size of the universe and one matter field. Appreciate the violence of that reduction. The honest arena has infinitely many dimensions, a coordinate for the geometry at every point of space, and mini-superspace throws away all of them except two. It is as if you tried to understand the world economy by tracking two numbers, the total amount of money and the price of one loaf of bread. Sometimes such caricatures capture the essence, sometimes they capture nothing. And the treacherous part is that the caricature cannot tell you which it is being. Every concrete number that comes out of quantum cosmology, every nucleation probability, every decoherence rate, comes out of this radical truncation. And the literature itself warns that the truncation is uncontrolled. No small parameter guarantees the discarded infinity of variables would not change the answer. When we quote quantum cosmology's results tonight, hear them all with this asterisk breathing behind them. Complication 3, and the most interesting. Buried inside the equation's geometry is a strange asymmetry. The natural metric on superspace, the DeWitt supermetric, is not positive in all directions. Exactly one direction comes with a minus sign, like the time direction of space-time itself, and that direction is the size of the universe. The equation with no time in it nonetheless singles out one internal variable that behaves like a time, the universe's own expansion. Tuck that clue away. It is the thread the recovery of time will eventually hang on. Pause here, on the summit of the strangest claim, and simply stand in it for a moment, because we have earned a breath before the descent. Around you, right now, the world is performing time with total conviction. Your heart is keeping its rhythm, dust is settling, somewhere a kettle is cooling. And 60 years of mathematical physics says that at the deepest level, the sum of all of it, the grand total state of everything, holds perfectly still. You now understand mechanically where that claim comes from. A symmetry, a constraint, a quantization, each step almost forced. What you cannot yet see is the way back, how a frozen totality can contain kettles that cool. Keep your own pulse in mind as we walk. It is about to become a technical term, because everything that follows asks one question with increasing precision. What, exactly, is your heartbeat beating against? But first, if the universe's state is a single frozen solution of h hat psi equals 0, which solution? An equation is only half of physics. The other half is the condition that picks the solution out. And for the wave function of the universe, that choice turns out to be nothing less than a theory of how existence began. Which is how, in 1983, the frozen equation produced the most famous wave function in cosmology, and one of the strangest scientific objects of the 20th century, the no-boundary proposal of James Hartle and Stephen Hawking. A word about the two men, because the pairing itself is a story. James Hartle was the quiet master of quantum cosmology's foundations, a physicist's physicist who spent his career asking what quantum mechanics even means when applied to the one system that contains all its own observers. Stephen Hawking, by 1983 already working through his synthesizer and students method as his body failed, needed no introduction then and needs none now. Together, they were attacking the most protected question in science, not how the universe evolved, but how to even write down its beginning without assuming something before it. Their question sounds impossible. What is the quantum state of a universe with no prior history to set it up? Hartle and Hawking's answer was geometric poetry. Compute the wave function, they said, by summing over all smooth four-dimensional geometries that have no initial edge at all. Spacetimes that are rounded off in the past the way the surface of the Earth is rounded off at the South Pole. Walk south and the surface simply, smoothly ends. Not at a wall, not at a rupture, but at a regular point where south stops meaning anything. In the no-boundary universe, the past closes off the same way. There is no first moment, no boundary where creation happened. The universe has no beginning edge, merely a smooth bottom, and asking what came before the beginning becomes exactly like asking what lies south of the South Pole. The question dissolves rather than gets answered. The technical move underneath the poetry deserves one honest sentence, because it is one of the boldest tricks in physics. The no-boundary sum is performed in imaginary time, a mathematical rotation in which time enters the equations exactly like a fourth direction of space, so that the sharp cone of a beginning can be smoothed into the rounded cap of a sphere. Whether imaginary time is a computational device or a glimpse of how reality actually closes itself off is a question Hawking teased his whole life and never settled. What the proposal delivers, concretely, is a definite wave function with checkable consequences. Fed through the machinery, it predicts primordial fluctuations with exactly the statistical character, the Gaussian, scale-balanced texture that satellites later photographed in the microwave sky. Its embarrassment is equally concrete. The same weighting favors universes with the least possible inflation, sitting awkwardly against the inflationary history our universe appears to have had. And the wave function is not even normalizable, a technical defect its friends and enemies both acknowledge. Alexander Vilenkin, a name viewers of this channel have met before, proposed the great rival in the same era: the universe as a quantum tunneling event, nucleating into existence the way a particle tunnels through a barrier it classically cannot cross, with only outgoing waves. Two candidate wave functions of the universe, both solutions of the same frozen equation, both answering which psi with a picture of origin. And here is the delicious, terrifying detail. The two proposals differ, in the simplest models, by a single minus sign in an exponent. One weight goes as the exponential of plus a quantity involving the cosmological constant, the other as the exponential of minus it. One sign. And that one sign flips the physical prediction from a universe born overwhelmingly likely to be empty and quiet to a universe born favoring violent inflation. Feel the scale of what hangs on that stroke of the pen. With the cosmological constant as tiny as our universe's measured value, the exponent inside those probabilities is astronomically large. So the two proposals do not mildly disagree. They disagree by a factor beyond all metaphor, each declaring the other's favoured universe absurdly improbable. Hartle and Hawking's weighting adores emptiness. Taken at face value, it says a universe like ours, having inflated richly, is a wild fluke, while handing a flawless account of the ripple's statistical texture. Vilenkin's weighting adores inflation. It births universes primed to expand exactly as ours apparently did, while its control over the resulting fluctuations is shakier. Each wave function explains beautifully what embarrasses the other. 40 years on, the field has not crowned a winner, and some of its sharpest current practitioners argue both proposals need replacement. Understand what this means for tonight's ledger. The frozen equation's boundary condition, the single choice that would specify which timeless universe we inhabit, is an open competition between two exponentials with opposite signs. We possess the equation of everything and cannot yet agree on its first input. The two deepest guesses about the initial condition of everything disagree by a stroke of the pen, and the literature admits, with unusual candor, that conventions and normalizations in this game carry acknowledged arbitrariness. The initial state of the universe is, today, a genuinely open question wearing two elegant proposals. So this is the situation the 20th century bequeathed: a master equation with no time, on an arena too big for rigor, computed in truncations too small for confidence, with rival boundary conditions separated by a sign. You might expect physicists to have recoiled. Some did. But the deeper response, the one that fills the rest of tonight, was better than recoil. It was a question. The question. If the fundamental equation has no time in it, then where does this come from? The second you just watched pass on your clock. A theory that deletes time must still explain clocks. It must explain why everything inside the universe, pendulums, heartbeats, strontium atoms, memories, behaves so flawlessly as if time flows. The frozen universe owes us an account of the thaw. And beginning in the 1980s, physics produced not one account but five distinct mechanisms by which time, real usable time, can emerge inside a universe whose total state never changes. They are the heart of this story, and the first of them was demonstrated, actually built in glass and light, on a laboratory bench in Turin, Italy, in 2013. Before the mechanisms, stand still for a breath and feel the size of what is being attempted, because recovering time is not a small repair. Everything you have ever called an event, every collision, every decay, every thought, is defined by when it happens. A physics without time is not missing a feature, it is missing the stage, the plot, and the tense of every verb. The recovery programs are attempts to show that the stage was never needed, that when can be rebuilt out of materials the frozen universe actually possesses: correlation, phase, entanglement, entropy. 5 workshops took up the challenge. Here is each one, honestly appraised. The idea is called relational time, and its founding paper by Don Page and William Wootters in 1983 carries one of the great titles in physics: Evolution Without Evolution. Here is their move, and I promise it can be said simply. Stop treating time as a river outside the universe. Ask instead, what do we actually do when we say something evolves? We compare it to a clock. Always. The coffee cooled in 10 minutes means, when the clock's hands stood here, the coffee was hot. When they stood there, it was cool. Every statement about time you have ever made is secretly a statement about correlation, about how one part of the world stands when another part stands somehow. Here is an image to carry into the mathematics. Imagine 2 wristwatches, quantum ones, manufactured entangled, their states locked in correlation from birth, and then sealed together in a box whose total contents, by construction, never change. An auditor outside the box, restricted to global questions about the whole box, finds every audit identical. The box is static, month after month. But now let the auditor ask a conditional question. Not, what is in the box, but, when watch 1 shows noon, what does watch 2 show? Suddenly structure pours out. When watch 1 reads noon, watch 2 reads noon. At 1, 1. The 2 dials march in lockstep through their correlations, an entire synchronized history, stored not in any motion of the box, but in the relationships between its parts. Nothing in the box ever moved. The box contains, timelessly, the full pattern of watch 2 given watch 1. And that pattern is indistinguishable from a story unfolding. Replace watch 1 with everything you call a clock, and watch 2 with the rest of the universe including you, and you have the proposal exactly. Page and Wootters took this seriously to the bone. Split the frozen universe into 2 pieces, call one piece the clock, and the other piece everything else. The total state, clock plus rest, is frozen. It satisfies the constraint, total energy 0, no evolution, exactly as Wheeler-DeWitt demands. But the 2 pieces are entangled, locked in quantum correlation. And now ask the only kind of question an inhabitant can ask. Given that the clock reads 3, what is the state of everything else? Then, given that it reads 4, 5? Page and Wootters proved the astonishing theorem. The sequence of conditional states of everything else, read against the clock, obeys exactly the ordinary Schrödinger equation, evolving in the clock's readings precisely as if a river of time were flowing. From outside, if an outside were possible, a static, changeless, entangled whole. From inside, correlations that are, in every operational sense, time. The flow is not in the state. The flow is in the relationship between the pieces. Time, in this picture, is not a container the universe sits in. Time is what entanglement looks like from within. 30 years later, physicists made it real. In 2013, at the Italian National Metrology Institute in Turin, a team led by Ekaterina Moreva and Marco Genovese built the page-wootters universe on an optical table. Their cosmos was two photons, two particles of light, prepared in an entangled state whose total energy satisfies exactly the frozen constraint. The toy universe's total state does not evolve. One photon was designated the clock. Its polarization slowly rotates, and reading it is reading a tiny dial. The other photon was the rest of the universe, and the experiment had two modes, which is the genius of it. In observer mode, the experimenters did what you and I do every day. They stood inside, measuring the universe photon against the clock photon. What they saw was a system in full quantum evolution. Probabilities oscillating against the clock reading, a running world, ordinary quantum mechanics unfolding. In super-observer mode, they measured only global properties of the joint two-photon state, the view from outside, the view no inhabitant can ever have. And from outside, the state stood still, static, frozen, unchanging across the whole experiment, exactly as the constraint demanded. One system, two questions. Ask it from inside and there is time. Ask it from outside and there is none. I will be precise about what this was and was not. A toy universe of two photons is an analogy machine, not a probe of quantum gravity. The published paper reports its results as demonstration curves, not as a battery of quoted precision statistics. The honest claim is qualitative, and it is still breathtaking. A frozen, timeless state built in a laboratory that contains, for those locked inside its correlations, a flowing time. The paper's authors opened their report with a 1600-year-old sigh from an ancient philosopher. What then is time? If no one asks me, I know. If I wish to explain it to one who asks, I know not. In Turin, for the first time, the sigh became an apparatus. And mark what kind of milestone that is in the long war between physics and philosophy. For 24 centuries, the nature of time belonged to the seminar room. Argued brilliantly, settled never, because no argument about time could be pointed at equipment. Page and Wootters changed the kind of question it is. Moreva and Genovese changed the kind of evidence it takes. However the great dispute finally resolves, the resolution will now have to pass through laboratories, and that migration, from endless debate to measurable proposition, is how every deep question in history has taken its first step toward an answer. I want to give you the texture of that apparatus because toy universe can sound like a metaphor, and this was hardware you could bump with your elbow. The photon pairs were born inside two thin crystals of barium borate, pumped by an argon laser running at 700 milliwatts. Filters selected light at 702 nanometers, deep red, just at the edge of what your eye could see. The clock's dial was rotated by a quartz plate less than a millimeter thick, stepped through 15 angles. A second, thicker plate implemented a refinement of the scheme proposed years later by theorists refining Page and Wootters' idea. The super-observer's all-seeing view was 16 distinct projective measurements, tomographically reconstructing the full joint state. This matters because of what physics is, not a book of assertions, but a chain of custody from idea to instrument. Time as entanglement began as a theorem in 1983. In 2013, it became count rates on detectors in Turin. A follow-up analysis even applied a test called the Leggett-Garg inequality to the toy universe's internal clock and found it violated, meaning the time inside the frozen state is genuinely quantum in character, not a classical dial smuggled in. Nor did the Turin experiment end the story. The mechanism has kept maturing. In 2021, a team including Caterina Foti and Alessandro Coppo published in Nature Communications a substantial deepening of the page-wootters framework. Using so-called generalized coherent states, the quantum states that most closely mimic classical behavior, they showed something remarkable. From a single global stationary state, conditioning on a quantum clock yields not merely Schrödinger evolution, but, in the appropriate limit, the classical equations of motion themselves. Ordinary deterministic physics, trajectories, orbits, the mechanics of Newton that began our story, emerging from a frozen, entangled state, with time as the reading of one subsystem by another, all the way up. The chain now runs unbroken in principle. Frozen state, to quantum evolution, to classical motion, each layer conditioned out of the one below. What began as a strange theorem in 1983 has become a research program with laboratories attached. And yet, honesty always, relational time did not conquer the field, because it carries unresolved wounds of its own. The sharpest critics, Carol Kuchar's chief among them, pressed on a technical nerve. The scheme struggles to define clean probabilities for sequences of measurements. Not what is the universe like when the clock reads 3, but given it was this at 3, what is it at 5? And those two-time questions make up most of real physics. Proposed repairs exist. Whether they fully succeed is genuinely contested. So hold page-wootters the way a careful physicist does, as a profound demonstration that a frozen state can contain an internal operational time, while the bookkeeping of that time remains an open construction site. And there is a subtler trouble stalking all internal clock schemes, catalogued with merciless thoroughness in the great canonical reviews of The Problem of Time by Carol Kucharz and Chris Isham in the early 1990s. Call it the embarrassment of choices. If time is to be read off some internal variable, the universe's size, a matter field, a clock subsystem, then which internal variable? The formalism offers many candidates, and the deep worry, documented across decades of attempts, is that different choices of internal clock do not in general yield equivalent physics. Quantize using one internal time, and you can get answers that disagree with the quantization built on another. Newton's river, whatever its faults, was at least unique. The recovered times of the frozen formalism come as a crowd of rivals, and no principle within the theory crowns one of them king. Perhaps decoherence effectively selects the winners. Perhaps the disagreements wash out in the simulation where we actually live. Both are argued, neither is proven. Add it to the honest ledger. The problem of time is not one problem, but a braid of them, and untangling one strand has a way of tightening another. Which brings us to the second recovery mechanism, the one most physicists quietly regard as the workhorse answer. The one that explains not a toy universe, but this one. It goes by an unlovely name, the Semiclassical emergence of time. And its central idea is one of the most beautiful reversals in physics. The clock that time emerges from is the universe itself. Remember the clue I asked you to tuck away? That inside the timeless equation, one variable behaves differently from all others. The size of the universe, carrying the lone minus sign in the DeWitt supermetric. Now watch what that asymmetry buys. The variables of the universe split naturally into two families. On one side, the geometry of space as a whole. Above all, the universe's overall scale. Heavy, slow, ponderous, the deep keel of reality. On the other, everything light and quick. Matter fields, radiation, the small fluctuations that become galaxies. In 1985, in work by James Hartle's collaborator Jonathan Halliwell together with Stephen Hawking, and in parallel lines by others, physicists applied to the wheeler-dewitt equation the same approximation chemists use when they separate the slow lumbering of atomic nuclei from the fast whirl of electrons. Write the frozen wave function as a rapidly turning phase governed by the heavy geometry, times a light remainder. Feed it into h hat psi equals 0, and two wonders fall out in successive orders of approximation. First, the heavy phase, on its own, obeys the classical equations of general relativity. A definite, classical, expanding spacetime crystallizes out of the timeless wave, not put in by hand, but extracted as the leading behavior of the frozen equation. Second, and this is the birth of time itself, the light, fast variables are found to obey an equation of their own, an ordinary time-dependent Schrödinger equation, complete with the IH bar d psi dt that the fundamental equation lacked. And the t in that recovered equation is not Newton's river restored, it is defined by the heavy phase. Time is the direction along which the universe's own expansion advances. Read that again. The expansion of the universe is not something that happens in time. At the fundamental level, the expansion is the clock, and what we call time is motion read against it. Physicists call it WKB time, or Sichel time. It is approximate, emergent, and derived, and it is, by wide consent, the best current account of why every laboratory Schrödinger equation on Earth works flawlessly with a t in it, inside a universe whose master equation has none. The corrections to this picture are even calculable. They enter suppressed by the square of the Planck mass, so colossally suppressed that no experiment yet reaches them. Time, in this account, is like the surface of the sea, perfectly real to every swimmer, while resolving at depth into something that is not surface at all. But the WKB story, powerful as it is, has a hole in the middle, and the honest naming of that hole leads directly to the third mechanism. The approximation explains how a classical spacetime and a Schrödinger clock can emerge. It does not explain why we see one definite emergence rather than a ghostly quantum blend of many. Worse, the frozen equation is completely symmetric between an expanding universe and its time reverse, a contracting one. The mathematics contains both, superposed with equal right. Why does your experience contain exactly one history, running in exactly one direction? The answer physicists assembled, chiefly Dieter Zeh, the father of decoherence theory, and his student Klaus Kiefer, is the same answer that explains why you never see a coffee cup both broken and whole: decoherence. If the word is new to you, here is its heart in one image. Quantum alternatives can interfere, overlap and interlace like ripples, only while they remain private, untouched, unrecorded. The moment information about which alternative holds leaks into the surroundings, a single scattered photon is enough. The interference is destroyed, as surely as a secret stops being a secret. And macroscopic objects cannot keep secrets. A dust grain in sunlight is struck by billions of photons per second, each one carrying away a partial record of where the grain is. The environment is a relentless press gallery, photographing everything, always. That is why the quantum strangeness of superposition never survives to the scale of cups and chairs. Not because some special law switches off, but because big things are informationally incontinent. They broadcast themselves, and broadcast kills interference. The universe's small, messy degrees of freedom, the countless tiny inhomogeneities, the gravitational ripples, the photons nobody tracks, act as an internal environment, ceaselessly monitoring the large ones. That monitoring destroys the delicate quantum interference between macroscopically different alternatives. The expanding branch and the contracting branch of the universal wave function decohere from each other almost instantly. Computed rates in model universes grow ferociously with size, so each branch proceeds internally as if alone. A definite, single, classical history is what a branch looks like from inside, after the environment has shredded its interference with the alternatives. And decoherence delivers one more gift, the deepest of all, the arrow. Zay observed that the Wheeler-DeWitt equation's internal structure is asymmetric in the universe's size. The interactions that entangle degrees of freedom switch off as the universe shrinks towards zero. Impose the simplest possible boundary condition, that at vanishing size, the universe's parts are unentangled, clean, uncorrelated, and entanglement, hence entropy, can only grow with expansion. Every arrow of time you know, why eggs break and never unbreak, why you remember yesterday and not tomorrow, why causes precede effects, why you age. Every one of them, in this account, flows from a single fact about one end of the universe. It began small, simple, and unentangled. The river of time, with its unmistakable current, is revealed as a gradient of correlation, running from an untangled beginning into an ever more tangled forever. When cosmologists apply this machinery to the primordial fluctuations, the decohered ripples come out with the amplitude, a few parts in 100,000, that satellites actually photograph on the microwave sky. The account is not idle philosophy. It touches the data. Count what this one boundary condition is being asked to purchase, because the inventory is your entire temporal life. Why do you remember breakfast and not tomorrow's dinner? Because memory is a record, records are correlations, and correlations accumulate in the direction of growing entanglement, the direction pointing away from the small, simple beginning. Why do causes precede effects? Same answer. A cause is a low entropy configuration whose consequences fan outward into higher entropy. The fan opens away from the beginning. Why does your coffee cool, your ice melt, your body age? Each is entropy increasing, and entropy increases because the universe started with so little of it. A downhill run that has lasted 13.8 billion years and is nowhere near its bottom. Why can you not unsay a word, unbreak a glass, unlive a day? Because reversing any of them would require gathering back correlations already scattered into billions of degrees of freedom, as hopeless as reassembling a dropped whisper from the acoustics of a stadium. One fact, the universe began small, smooth, and unentangled, and every irreversibility you have ever suffered follows as bookkeeping. Physics does not currently explain why the beginning was so special. That remains one of cosmology's deepest open wounds. But it has traced every arrow in your life back to that single archery stand. One clarification: the frozen formalism is owed before the next mechanism, because a lazy version of tonight's story circulates and it is wrong. The claim is not that motion is fake, that pendulums secretly hang still and rivers secretly do not run. Inside the recovered, saxical, decohered world, the world every experiment inhabits, motion, change, and duration are as real as anything gets, measured, predicted, confirmed to 19 decimal places. The freeze is a statement about the total and about fundamentality, about what the whole is doing when no part is asking, and about which concepts survive to the deepest level of description. Compare temperature. Fundamentally, there is no such thing as the temperature of an atom. Temperature is a collective property that emerges from countless motions. And yet your fever is real, your coffee genuinely burns, and thermometers are not lying. Nobody says heat is an illusion, they say heat is emergent. The mainstream position on time is precisely parallel, real at every scale you will ever touch, and absent from the foundation. When a headline says physics proved time is an illusion, it has flattened that careful layered claim into nonsense. The claim is stranger and more disciplined. Time is real the way temperature is real, which is to say, real and not fundamental. The fourth mechanism is the strangest, and I give it to you partly because its authors include one of the great living mathematicians. Its co-author has spent a career preparing physics for exactly this deletion. Carlo Rovelli, co-founder of Loop Quantum Gravity and the field's most eloquent public voice for the unreality of fundamental time, once titled a research paper in full seriousness, "Forget Time." His counsel to physics in that paper is tonight's whole arc compressed to a directive. Stop trying to find the time variable in quantum gravity because there is none to find. Formulate the theory relationally, correlations between physical quantities, and let time be a word we recover afterward for the patterns that behave like clocks. It is the boldest methodological wager in the field that the way past the problem of time is straight through it, surrendering the concept entirely at the fundamental level. In 1994, Ravelli joined forces with Alain Connes, winner of the Fields Medal, mathematics' highest honor, to propose the thermal time hypothesis. Their starting point is a jewel of pure mathematics called the Tomita-Takasaki theorem, and its physical reading is almost scandalous. Take any quantum system described statistically, described that is by a thermal state, the way you describe anything whose microscopic details you cannot track. The theorem says that state, by itself, generates a unique preferred flow, a one-parameter unwinding of the observables, mathematically inevitable, singled out by the state alone. Connes and Ravelli's proposal, that flow is time. Time is not fundamental. The deep universe needs none. Time is what a thermal state feels like from inside, the automatic unwinding generated by your own coarse-grained, heat-blurred description of the world. In their formula, physical time and temperature are locked together. The flow of time is the modular flow of the thermal state, rescaled by temperature. Heat and time become two faces of one fact. You experience duration because you are warm, which is to say, because you are ignorant of almost everything, which is to say, because you are a subsystem. A being with complete microscopic knowledge of a frozen universe would, on this view, have nothing flowing at all. The hypothesis even reaches out and touches one of the most celebrated results in theoretical physics, the Unruh effect, the prediction that an accelerating observer, rushing through what an inertial observer calls empty vacuum, experiences that vacuum as a warm bath of particles. In the thermal time reading, the Unruh temperature acquires a startling identity. It is precisely the ratio between the observer's thermal time and their proper time, the exchange rate, so to speak, between the flow their state generates and the flow their wristwatch counts. Where the two flows match, temperature is what mismatch would feel like. The hypothesis remains a minority elegance. Its link to ordinary proper time is still being worked out, and its meaning away from equilibrium stays murky. But notice how its punchline rhymes with everything tonight. Time keeps emerging not as a property of the universe, but as a property of limited perspectives on the universe. The river keeps turning out to be the riverbank's opinion. And the fifth voice belongs to the purest heretic of them all, a man who looked at the frozen equation and, rather than rescuing time, accepted the freeze with open arms. Julian Barbour is a British physicist who deliberately built his career outside the university system, supporting himself translating Russian scientific journals from a farmhouse near Oxford so that no fashion could tell him what to work on. He spent 5 decades arguing that the wheeler-dewitt equation is not a problem to be solved, but a truth to be believed. His book, The End of Time, published in 1999, states the position without flinching. Time does not exist. What exists for Barbour is a vast, timeless landscape he calls Platonia, the collection of every possible configuration of the universe, every arrangement of everything, each one a single frozen now. Nothing moves through them, nothing connects them. They all simply are, the way every page of a book exists at once. The machinery beneath Barbour's vision is called best matching, and it is disarmingly concrete. Given 2 configurations of the universe, 2 frozen nows, how similar are they? Barbour's rule? Slide, turn, and rescale one against the other until they overlap as closely as possible, and call the residual difference their intrinsic distance. No clock is consulted. No external space is assumed. Configurations are compared directly, shape against shape, the way you might compare two photographs by laying one over the other. From this single operation, he and his collaborator Bruno Bertotti showed in 1982 the dynamics of Newtonian physics can be rebuilt, and its descendants reconstruct Einstein's, without absolute time ever entering. The mature program, shape dynamics, goes further and strips away absolute size as well. Only pure shape survives as fundamental, with the universe's story a path through the landscape of shapes, parameterized by nothing. What of our vivid experience of flow? Barbour's answer is the concept he calls time capsules. Some configurations, some single frozen nows, happen to contain internal structures that look like records of a past. Memories in brains, rings in trees, light en route between stars, half-played chess games. A now like that feels, from inside, like the latest moment of a long history. But the history is an inference drawn entirely from present structure. You believe in your past, Barbour points out, on the evidence of present configurations only. Present memories, present photographs, present documents. He is right about that, and it is worth an uncomfortable pause. Everything you take as proof that time passed is, strictly, a feature of the arrangement of matter now. Barbour's universe is the frozen equation taken at its word, an unmoving gallery of nows, some of which are so richly self-referential that they dream a river. Few physicists follow him all the way. Nobody has managed to prove him wrong. And his framework, relational, timeless, built on comparing configurations directly, matured into an active research program called Shape Dynamics, in which even size is stripped away and only pure shape remains. When the man has been asked what, then, we perceive, his answer has the cold clarity of the equation itself. It is change we perceive occurring all around us, not time. Notice also what the five mechanisms quietly agree on, despite their rivalries, because the agreement is tonight's real inheritance. Every one of them locates time in a relationship: system and clock, phase and matter, branch and environment, state and observer, configuration and record. Not one of them locates time in the universe alone, standing by itself. Whatever else remains open, 60 years of assault on the frozen equation have converged on this. If time exists at all, it is not a solo performance. It takes two. So there is the recovery operation, 5 expeditions deep. Relational time. The flow is entanglement, read from inside, built and observed in Turin. Semiclassical time. The expanding universe is itself the clock, and the Schrödinger equation re-emerges beneath its phase. Decoherence. Branches shred their interference, and a low entropy beginning gives the single surviving history its arrow. Thermal time. Duration is what being a warm, ignorant subsystem feels like. And Barbour's refusal: there is nothing to recover, only frozen nows that contain their own apparent histories. 5 mechanisms, overlapping and rival at once, and notice the family resemblance that unites the first 4. In every one, time is real for parts, absent for wholes. The universe does not have time, subsystems do. You are not in a river, you are the river, locally, because you are a piece of the frozen whole correlating with other pieces. That is the mainstream's considered answer to the problem of time as it stands tonight. But it is not the only answer standing. Because a serious, credentialed, unbowed minority of physicists looked at this entire edifice, the frozen equation, the emergent clocks, the timeless whole, and said, no. The equation is not telling us time is an illusion. The equation is telling us we quantized the wrong thing, or trusted the wrong theory too far. Time, they argue, is not emergent. Time is fundamental. More fundamental perhaps than the laws themselves. And their counterattack comes armed with something the timeless camp rarely offers: predictions that can die. Meet the first insurgent, lee-smolin, one of the founders of loop quantum gravity, who spent the first half of his career deep inside the timeless formalism, and then, publicly, spectacularly, changed his mind. His 2013 book carries the thesis in its title, Time Reborn. Smolin's argument begins with a challenge to the whole way physics thinks. Timeless physics, he observes, works beautifully for subsystems, a pendulum, a planet, a particle beam, because we stand outside them, holding the clock. But the universe has no outside. Extending the timeless method from subsystems to the whole cosmos, Smolin argues, is an unjustified leap, the cosmological fallacy, he calls it. His alternative inverts everything. Time is the one thing that is truly fundamental, real, global, flowing, and it is the laws of physics that are secondary, evolving in time the way species do. And here is what makes Smolin more than a philosopher. He built a mechanism and staked it on a number. His proposal of cosmological natural selection, published in 1992, imagines that black holes spawn new universes, that the collapse at a black hole's heart bounces into a fresh expansion, a daughter cosmos with slightly mutated physical constants. Universes that make many black holes have many offspring. The constants we observe would then be tuned, Darwin style, for black hole production. You may find that picture wild, but notice what it requires: a real, irreversible, generational time ordering across universes, mothers before daughters. And notice what it does that timeless proposals rarely do: it predicts. If our constants are tuned to maximize black holes, then certain adjustments must not be able to increase black hole production. And from this, Smolin derived a hard, falsifiable number. The heaviest possible neutron star should weigh no more than about 1.6 times the mass of our Sun. He wrote, in print, that observations could easily kill the theory. They very nearly did. In 2010, a team of radio astronomers led by Paul Demarest, using an exquisite relativistic timing effect called the Shapiro delay, weighed the neutron star PSRJ 1614-2230 and published the result in Nature. 1.97 solar masses, plus or minus 0.04. By far the heaviest neutron star reliably measured to that date, sitting decisively above Smolin's stated limit. Watch carefully what happened next, because this is science behaving properly in public. Smolin engaged the measurement in print, noting the ways the bound might flex, conceding that still heavier confirmed masses would be inconsistent with the prediction. Whatever you conclude about cosmological natural selection, and its standing today is pressured, contested, wounded but not formally buried, Smolin did the thing the timeless camp is structurally unable to do. He put fundamental time on the table as a hypothesis with consequences, attached a number to it, and let the sky take its shot. The theory's other wounds deserve their sentence too, in fairness. Leonard Susskind argued that eternal inflation, if real, manufactures universes vastly faster than black hole reproduction ever could, swamping the Darwinian signal. And the physicist-philosopher John Polkinghorne pressed on the deepest joint, that ordering universes into generations requires a consistent time across universes, the very kind of supertime that relativity gives us no license to assume. Smolin's answer, characteristically, is that this is precisely his point. Take time seriously enough as fundamental, and such an ordering is not an embarrassment, but the first honest posit. The argument continues, in print, unresolved, which is what arguments between serious people look like. The second insurgent does not merely assert that time flows. He proposes that its flow is literally the construction of the universe, one atom of space-time at a time. Raphael Sorkin's causal set theory, founded in a 1987 paper with Luca Bombelli, Johann Lee, and David Meyer, begins by taking discreteness seriously. Space-time, at the deepest level, is not a smooth continuum, but a locally finite scatter of elementary events, connected by one relation only. This event is to the causal past of that one. Order plus number equals geometry runs the program's motto. From nothing but the causal ordering and the counting of elements, the smooth space-time of Einstein is supposed to emerge at large scales, the way a photograph emerges from pixels. Then, in 1999, Sorkin and David Rideout added the engine that concerns us tonight, a dynamics called classical sequential growth, in which the causal set is not given all at once, but grows. New elements come into being, one after another, each born to the future of some of those already present, with probabilities governed by fixed rules. And the authors say, with striking, unhedged plainness, what they take this to mean. We do not think of the process as happening in time, but rather as constituting time. Read that twice. In causal set theory, the passage of time is not an illusion painted on a frozen block, and not an emergent bookkeeping of correlations. The passage of time is the ongoing birth of reality, becoming elevated to physics. The present is where the construction has reached. The future does not exist yet, not even as a block awaiting your arrival. It is the most direct possible negation of the frozen formalism, proposed not by a mystic, but by one of the most mathematically rigorous programs in quantum gravity. And the program, along the way, produced one of the field's quiet triumphs. Years before observation, causal set reasoning anticipated the correct order of magnitude of the cosmological constant, one of very few frameworks that can make that claim. Give causal sets one more minute, because its central slogan hides a genuine astonishment. Order plus number equals geometry claims that the two most primitive notions imaginable, which events can influence which, and how many events there are, suffice to rebuild everything geometric: distances, durations, curvature, the whole apparatus of Einstein. Duration between two events? Count the longest chain of elementary happenings connecting them. Time as literal counting, like rings in a tree. Volume of a region? Count the events inside it. The continuum you perceive would then be exactly like the smooth surface of a photograph, an artifact of not looking closely enough at something fundamentally dotted. And the program earned its keep with one of the strangest successes in modern cosmology. Reasoning from the expected statistical fluctuations in the count of spacetime atoms, Sorkin argued, years before the 1998 supernova observations stunned astronomy, that the cosmological constant should be not exactly zero, but tiny and non-zero, with roughly the magnitude later measured. A theory built on time as becoming, called the size of dark energy's push in advance. That does not prove the universe grows. It proves the growers must be taken seriously. The third insurgent commits the most direct heresy of all. He rebuilds physics with a preferred time nailed back into place. In 2009, Petr Hořava, a Czech-American string theorist, proposed a theory of quantum gravity now called horava-lifshitz gravity, whose central move is to break the very symmetry that killed time in the first place. Remember the causal chain of tonight's whole story. Einstein's theory refuses to prefer any slicing of spacetime. That refusal forces the Hamiltonian to vanish. The vanished Hamiltonian freezes the wave function. Hořava attacks the first link. At extreme energies, he proposes, space and time do not enter symmetrically. They scale differently, time counting triple, in a precise technical sense, against space, so that the theory admits extra spatial structure while keeping its equations tame in time. The reward is remarkable. The modification cures exactly the mathematical disease that makes quantum gravity infamous. The theory becomes renormalizable by power counting, its graviton propagator softened at high energies. The price is exactly as remarkable. The theory carries a physically preferred foliation of spacetime, a real structural cosmic time, restoring by decree what general covariance abolished. In Hořava's world, the wheeler-dewitt freeze never happens, because the symmetry that caused it was only ever an approximation of low energies. The technical signature of the trade is worth hearing even without its algebra. In Hořava's theory, the equations of motion are permitted up to 6 derivatives in space, capturing wild short-distance spatial structure, while remaining strictly second-order in time, the tame form that keeps a theory free of the runaway instabilities that plague higher time derivative physics. Space absorbs all the ultraviolet violence. Time is kept gentle by decree. That asymmetry is the whole design, and it is also the whole cost, because nature has been checked for exactly this kind of asymmetry with ferocious precision. Observations of light and particles arriving together from cosmic distances constrain violations of relativity's space-time symmetry to extraordinary depth. Hořava's theory must thread that needle while its extra degrees of freedom behave. The theory has real, known troubles: an extra propagating mode that refuses to decouple cleanly, strong coupling worries, and that tight experimental leash. And its standing today is active but embattled. Yet its existence proves something bracing. The timeless conclusion is not forced on physics. It is forced on a particular quantization of a particular reading of relativity. Change the reading, and time walks back in through the front door, wearing mathematics as sound as anything in the timeless camp. And in the middle of this war stands loop quantum gravity, the program that grew from Abe Ashtakar's 1986 reformulation of general relativity in variables that made the impossible constraints suddenly tractable. Loop quantum gravity belongs to the canonical wheeler-dewitt tradition. Its states still satisfy constraint equations, its deepest formalism still lacks external time, and yet what it found inside those equations changed the texture of the debate. Applying the quantization to geometry itself, Ravelli and lee-smolin, allies then, before their views of time diverged, derived in 1995 that area is quantized. Space itself comes in indivisible grains. The possible areas of any surface form a discrete ladder, computed by an exact formula, 8 pi, times a constant called the barbero-immirzi parameter, times the Planck length squared, times the square root of j times j plus 1, where j counts in half-integer steps. The meaning under the symbols: there is a smallest possible patch of area, around 10 to the minus 70 square meters, and no measurement can ever return less. Space is not a continuum. It is a fabric of quantum threads, and the states of geometry are networks of spin, graphs whose edges puncture surfaces and deposit quanta of area where they pass. Let the numbers of that granularity land, because they are among the most extreme in science. The fundamental grain is set by the Planck length, about 1.6 times 10 to the minus 35 meters, and the smallest possible non-zero area comes out around 10 to the minus 70 square meters. To feel that, a single proton is as many orders of magnitude above the Planck scale as you are above the proton. The grains of space are as far below an atomic nucleus as a human being is above it. And there is a seductive numerological coda the honest narrator must flag as calibration rather than prophecy. If the theory's one free parameter is fixed by demanding that black hole entropy come out right, Bekenstein and Hawking's quarter of the area law, then the smallest quantum of area becomes exactly 4 times the natural logarithm of 2 in Planck units. 1 bit of information per elementary puncture of a surface. Wheeler's late-life slogan, "It from bit," materializing in his own student's formalism. Beautiful, and, to be scrupulous, a consistency choice, not an independent prediction. The parameter is set by hand to make the entropy match. Feed the granularity into cosmology and the Big Bang singularity. The infinite density catastrophe where classical time begins dissolves into a big bounce, a prior contracting phase, crushed to the density where the grains of space push back, rebounding into our expansion. Even here, in the heart of the timeless tradition, the story bends toward histories and befores. The equations freeze. The physics they describe keeps insisting on narrative. Before we tally the board, notice the strange kinship binding the three insurgents, because it sharpens what the war is actually about. Smolin, Sorkin and Hořava disagree about nearly everything: evolving laws, growing atoms of space-time, broken symmetries. But they share one conviction the timeless camp denies: that becoming is real. That the universe is not a completed four-dimensional fact, but an unfinished performance. That now is not a perspective, but an event. That the future's absence is not a feeling, but a physical truth. Strip away the mathematics, and the two camps are arguing about whether reality is a noun or a verb. The frozen formalism says noun, a state, complete, self-consistent, containing all its apparent histories the way a novel contains its chapters. The insurgents say verb, a happening, still happening, whose next chapter does not exist in any drawer. Physics has argued nouns against verbs before, particles against waves, being against becoming, all the way back to the Greeks. What is new, what is genuinely unprecedented about the last 60 years, is that the argument now runs through published equations, laboratory photons, and a neutron star's weighed mass. The oldest question in philosophy has become a research program with error bars. So the board is set, and you should see it whole. On one side, the frozen formalism and its recovery mechanisms, time as entanglement, time as the universe's own expansion phase, time as decoherence plus a low-entropy dawn, time as thermal perspective, or Barbour's gallery of self-dreaming nows. On the other, Smolin's evolving laws under a fundamental time, Sorkin's universe constituting time by growing, Hořava's restored cosmic foliation. Between them, loop quantum gravity's granular space, feeding both camps ammunition. Every one of these is serious physics, authored by architects of the field, published in its flagship journals. And every one of them agrees on a single staggering fact that no textbook shouted at you in school. Nobody currently knows whether time is fundamental. The naive quantization of our two best theories says it is not, says it in one line, h hat psi equals 0, an equation so plain a child can copy it, and so deep that half a century of genius has not finished absorbing it. And now let the whole argument come home, out of the journals and into the room where you are sitting, because the frozen equation is not really about equations. It is about the second you watched pass at the start of this video, about what that second was. So let us ask the questions you actually care about, and answer them with exactly as much honesty as the physics permits. Does any of this mean the past still exists, that your childhood is not gone but merely elsewhere? Here is what can be said with discipline. In the picture the recovery mechanisms paint, the fundamental description contains no moving spotlight of now, no marker that selects one moment as the real one and demotes the rest. The sense of a unique present is generated by each subsystem from inside. Every moment's inhabitants feel their moment to be the living one, precisely as you now feel yours. On that reading, your past is not annihilated behind you. It simply does not need annihilating, because behind you was never a place. But hear the caveat at full volume. Sorkin's growing universe says otherwise. There, the past has genuinely finished being built, and the future genuinely has not, and physics cannot currently adjudicate. What physics can say is narrower and stranger. Nothing in the fundamental equations requires the past to have stopped existing. The extinction of your yesterdays is a feeling, not a theorem. Then is the future already fixed? Is everything you will ever do sitting frozen in the block, waiting? Careful. Even in the fully timeless reading, what exists is a quantum state, and a quantum state is not a script of outcomes. The recovered time inside it carries quantum mechanics' irreducible openness with it wherever it goes. Timeless does not mean predetermined in the classical sense. The frozen whole contains structured possibility, not a finished transcript of your choices. And if lee-smolin and Sorkin are right, the future is not merely open, it is absent, unconstructed, a thing the universe has not yet done. Between your future exists as unresolved quantum structure and your future does not exist at all, physics is honestly split. What no serious side offers is the fatalist's comfort or the fatalist's despair. Nobody's equation reads your tomorrow aloud. One more question belongs in this set, because a sharp viewer will have been holding it for an hour. If time is emergent, cooked up locally by correlations and coarse graining, why is it so consistent? Why does your kitchen clock agree with the atomic clock in Boulder, with the pulsars in the sky, with the decay of every muon in every cosmic ray, all ticking in one coherent concert? Would not a merely emergent time be patchy, different here and there, like weather? The emergent picture has an answer, and it is quietly elegant. All those clocks are subsystems of one universe, correlated through one shared history, reading their time off the same underlying structure, the same semiclassical phase, the same entropy gradient, the same expanding geometry. Their agreement is no more mysterious than the agreement of 1,000 shadows about the direction of one sun. Indeed, where the underlying structure varies, the clocks do disagree. That is precisely what Haffel and Keating measured on their airliners, and what Boulder reads across a centimeter of height. The concert has local tempo changes exactly where relativity says the conductor's geometry changes. Emergent time is not patchy weather. It is a single climate, because there is only one universe generating it. And the question under all the others, why do you feel the flow, the unmistakable current carrying you through this very sentence? Assemble tonight's pieces and a candidate answer emerges with disquieting completeness. You are a subsystem, warm, macroscopic, and entangled with everything around you. Being warm, your description of the world is thermal, and thermal states generate flow. Being macroscopic, you decohere. Your alternatives shred their interference, leaving you one definite history. Being entangled with the low entropy gradient of an expanding universe, your records accumulate in one direction only. You contain memories of the small universe side of history, and none of the other, because that is the side correlations grow from. A being with those three properties, the argument runs, would feel exactly what you feel: a vivid now, a fixed past, an open future, a current. The flow in this account is not out there ticking. The flow is what it is like to be a certain kind of subsystem. When I first sat with that, genuinely sat with it, the vertigo was not that time might be an illusion. It was that the illusion, if that is what it is, would be indistinguishable forever from the inside, from the river Newton promised. Your experience is real either way. What hangs undecided is only what your experience is of. So where does the evidence, honestly weighed, actually stand? Let me give you the synthesis as the field's own literature gives it, in layers of decreasing confidence. Layer 1. Robust. At the level of our tested theories, Newton was wrong. Time is not absolute, not universal, not a river outside events. Clocks on jets, satellites, and centimeter-high shelves prove it daily. Layer 2. Mainstream and firm. When general relativity is quantized canonically, the time variable disappears from the fundamental equation. This is not speculation, but derivation, the direct consequence of the theory's own symmetry. Layer 3. The working consensus. Ordinary flowing time re-emerges from the timeless equation as an approximation, through the semaphore expansion read against the universe's own growth, sharpened into a single directed history by decoherence anchored to a low entropy beginning, and mirrored in miniature by the Turin photons. This layered picture, timeless at bottom, temporal on top, with the flow belonging to subsystems rather than to the whole, is, as best I can report it, the closest thing modern physics has to an official position on time. And layer 4, genuinely open, whether that official position is true, whether the deepest level really is timeless, or whether lee-smolin, Sorkin, and Hořava are right that the freeze is an artifact of quantizing the wrong theory, is undecided. It may remain undecided until physics reaches the Planck scale, 13 orders of magnitude beyond our most powerful accelerators, where the answer actually lives. You might reasonably ask how physics functions at all with a crisis like this at its root, and the sociology of the answer is its own lesson. The working physicist measuring particle lifetimes at CERN, the astronomer timing pulsars, the engineer synchronizing satellite clocks. None of them consults the wheeler-dewitt-equation before breakfast, and none of them needs to. Their time, laboratory time, subsystem time, the recovered T of the SEIMD world, works flawlessly in its domain, the way Newton's gravity still lands spacecraft in a universe that is actually Einstein's. Foundations and practice run on different clocks, in every sense. But do not mistake the calm for resolution. Physics has lived before with quiet cracks in its foundations. The ultraviolet catastrophe that birthed quantum theory, the ether that birthed relativity. And the lesson of history is consistent. The cracks do not close on their own, and the theories that finally close them redraw everything. The problem of time is precisely such a crack, patient and load-bearing. Every physicist tonight can ignore it. Physics itself cannot forever. And what observation could ever close it? Map the battlefield honestly. The freeze itself lives at the Planck scale. Energies 10 million billion times beyond the Large Hadron Collider, where no conceivable accelerator reaches. That door is shut for centuries, if not permanently. But the war has proxies. Hořava's restored cosmic time requires broken relativistic symmetry, and broken symmetry leaks into the low-energy world. So every ultra-precise test of relativity, every simultaneous arrival of light and gravitational waves from a distant catastrophe, tightens the leash on fundamental time theories of that kind. A genuinely live front, active right now. Causal set discreteness may smear the propagation of the highest energy photons across cosmic distances, searched for, so far silent. The initial condition, Hartle-Hawking against Vilenkin, presses its signature into the primordial fluctuations, where next-generation microwave and gravitational wave observatories will read finer print than Planck could. And the quantum clock laboratories that began in Turin keep scaling upward, entangling ever larger systems into ever better toy universes. None of these will hand down the final verdict on whether the deepest level ticks. Each can eliminate contenders. That is how this question will move, not by one decisive experiment, but by a tightening ring of survivals and executions, the way physics has always chosen among its futures. Return one last time to Boulder, Colorado, because the clock deserves the final measurement of the night. Follow its lineage and you watch our species close in on time like a hunter. By 2015, optical clocks had reached parts in 10 to the 16. By 2019, 2 in 10 to the 18. In 2022, a JILA team resolved Einstein's gravitational time dilation across a single millimeter, the thickness of a fingernail's edge. And in 2024 came the 8.1 times 10 to the minus 19 machine, reading the gradient of time across a centimeter of height as routinely as a carpenter reads a level. Project the trend and it only sharpens. We will measure time ever more exquisitely, and every improvement will deepen, not resolve, tonight's paradox, because the paradox was never about measurement. The clock measures flawlessly the emergent surface, the correlations, the decohered branch, the thermal flow, the phase of an expanding universe. Whether anything ticks beneath the surface is a question no clock can answer. because every clock we will ever build is itself a subsystem, warm and entangled, standing on the surface it measures. The most precise instrument in human history and the deepest equation in human physics will keep staring at each other across this gap. One reading time to 19 decimal places, the other insisting there is nothing to read. There is a human coda to the equation itself, and it belongs in the record. Bryce DeWitt, who wrote the frozen equation, spent his later decades ambivalent about the fame it carried. The folklore of his exasperation with it survives in the community's telling, even as the equation anchored his field. John Wheeler, whose superspace vision demanded it, drifted in his last years toward an even stranger slogan: it from bit, existence from information, as if suspecting the deletion of time was only the first deletion. Julian Barbour, farming his timeless Platonia outside Oxford, found in the same symbols a kind of serenity. And lee-smolin, who helped build the timeless tradition's sharpest tools, walked out and declared the foundation itself mistaken. 4 minds of the first rank, one short equation, and no agreement on what it means, only agreement that it will not go away. The equations, as one of tonight's sources put it, are firmer than their interpretations. H hat psi equals 0 has outlived its author, most of its critics, and every attempt to dismiss it. Whatever time turns out to be, that line of symbols is now a permanent resident of physics, the shortest sentence ever written about everything. So gather the whole journey into one held breath. You began with a clock and a certainty: time passes. Newton wrote the certainty into law. Einstein bent the law until clocks on airplanes and centimetre-high ledgers disagreed on schedule. Then Arnovit, Deser and Misner sliced space-time, and the slicing confessed that general relativity's engine of time, its Hamiltonian, is a constraint pinned to 0. Bryce DeWitt turned the crank of quantization, and in 1967 the confession became the master equation. H hat psi equals 0, the Schrödinger equation with its time side amputated, a universe whose total state cannot change. Quantum cosmology took the frozen equation and asked it for the beginning of everything, and received 2 answers separated by a minus sign: Hartle and Hawking's smooth South Pole dawn against Vilenkin's tunneling flash. Then came the recoveries, time reborn as entanglement in Turin's 2-photon universe. Time reborn as the phase of cosmic expansion in the Semiclassical expansion. Time given its arrow by decoherence flowing out of a small, untangled beginning. Time as the thermal signature of being a warm and partial observer. And Barbour's refusal, the gallery of frozen nows, each dreaming its own history. Against them all, the Insurgents. Smolin's evolving laws staked on a neutron star's mass. Sorkin's universe that grows its own time atom by atom. Hořava's outlawed and rebuilt cosmic foliation, with loop quantum gravity's grains of space glittering between the camps. That is the state of the art on the deepest question a clock can raise. Physics wrote down an equation for everything, and time was not in it. And physics has spent 60 years discovering that putting time back is either unnecessary or impossible, or the whole point, depending on which of its greatest living minds you ask. Which leaves the honest edge, stated exactly. Physics can write a timeless master equation, and physics can show how ordinary time re-emerges from it as a superb approximation. Turin demonstrated the principle in light. What physics cannot yet do is tell you what the flow you are feeling right now actually is. The flow carrying you through this sentence, toward the end of this video, into the rest of your evening. It cannot say whether that flow is a fundamental feature of reality or a consequence of your being a warm, entangled, low-entropy subsystem of a frozen whole. No experiment currently proposed can decide it. The answer lives at the Planck scale, 13 orders of magnitude beyond our reach, or in the initial condition of the universe, which we can model but never rerun. Between the timeless block and the growing now, the evidence ends, and tonight, so does the certainty you started with. If a journey like this one is what you come to this channel for, all the way down, no shortcuts, honest about where the floor gives out, subscribe and bring a friend who still believes in absolute time. There is a whole cosmos of these questions left, and we are going to walk every one of them together. If a child ever asks you what time is, you now hold the strangest honest answer available to our species. You could say, time is what clocks measure, true and empty. You could say, time is the fourth dimension, true and misleading, since it is so unlike the other three. Or you could kneel down and say the real thing. Nobody knows. We know it bends. We know it runs slower in valleys than on hills, slower on fast airplanes than in quiet kitchens. We have measured it more precisely than anything else humans have ever measured. And when we wrote our deepest equation about the whole universe at once, time was not in it. So either the universe holds still while its pieces tell each other stories of motion, or the universe is still being built, one moment at a time, and nobody can yet say which. A century ago, that answer would have been scandal. Today, it is simply the state of the art, spoken plainly. The child will blink and ask what's for dinner, and that question, at least, still has an answer that flows. The clock on your wall is still ticking. Look at it once more, but look with tonight's eyes. Each tick is the most precisely measured phenomenon in human history, and the deepest equation we possess does not contain it. Somewhere beneath that ticking, either a universe is being built one atom of time at a time, or a frozen wave is dreaming, through you, that anything ticks at all. Both possibilities are open. Both are extraordinary. Both are, tonight, fully compatible with every measurement ever made. And the second you just spent hearing this sentence, whatever a second truly was, is yours and always will have been. Sleep well tonight, in whatever it is that carries you from tonight to tomorrow. Good night.